Hi everyone, welcome to the last session of the day. Oh, they increased my mic volume, that's cool. Gives me great pleasure to introduce our next speaker, Hugh Blemings, who's been around, I think, quite from the start of LCA, is that right, Hugh?
Yeah.
Right from the very start. So.
Slow learner.
And today he's talking about open and high performance computing. Please welcome Hugh Blemings.
Thank you for that kind welcome. I would like to follow the protocol and acknowledge that grateful to meet on the traditional, that we're meeting today on the traditional lands of the Yugambeh people. I pay my respects to their elders past and present and leaders that are emerging. So I'm going to talk about fast computers, and I'm mindful that without really realising it, by putting high performance computing in there, it connotes HPC or supercomputers, which while we'll talk about that, the question I'm hoping to walk us through today is how close can we get to truly open and fast computers, both now and in the future. And I mean open here in the sense of visibility, our ability to entrust our data to it, and with the growing and appropriate focus on data mining and that sort of thing, both that we're conscious of and that we're not so conscious of. I think this is a pretty timely kind of a thing. So we're not talking necessarily about fully trusted systems a la something like SEL4, which is a whole more level of greater complexity and a very valid discussion, but that's not what this talk is about. So I guess the fast distinction here is really as much about the general purpose computers as distinct from, say, embedded or specific purpose computing devices. I want to look a little bit at some timelines, and in the first instance in particular for free software. Just bear with me for one moment. I'm going to adjust this screen slightly so my eyesight is not as good as I thought it once was. The free and open source software timeline that I put up here is clearly a bit of a selected one. I guess you could trace back to 76 and Emacs as being when a lot of things started, the GNU project in 1985. But the Linux kernel is kind of where it really first came to my attention, and Linus's famous quote about sort of working on this little project that would never get terribly big or terribly serious. One might question whether it is terribly big or terribly serious now, perhaps. But the particular time points I wanted to call out here is the first ports of the Linux kernel to non-x86 architectures in 95. We saw the first port of Linux to PowerPC, as it was then in 1996 by Kurt Dugan and others. 1999, we saw Linux ported to PowerPC 64 by a number of people in this room, Paul McCarrison and others, and that was the IBM Power 4 CPU. But I guess what I was actually trying to call out as much as anything is I think 2008 is around the point where we kind of got lit to Linux being business as usual. Prior to that, there's a few other intermediate steps like the Debian project, 93, very important, commercial distros, first Ubuntu, released in 2004. But we can sort of paint that 2008, I think, is about the inflection point for open and free and open source software, where Linux has kind of become the default for our computing infrastructure. And in that process, I think it's fair to say that we've established that openness in software is really the best way to build secure systems. So openness is kind of a key part of this. What about open hardware? Well, open hardware's had a similar timeline, and actually doesn't quite stretch back as far. There's been a number of pretty pivotal moments for open hardware as well. Bruce Perrins kicked off the open hardware certification program in 97, 2005. Was the Arduino project, things like that. But as we are in those early stages of open hardware, we've largely been dealing with open hardware in the context of embedded or peripheral space rather than general purpose computing. As we progress along, the TAPA open hardware license was perhaps one of the most significant early stages of open hardware, being one of the first recognised licenses for open hardware that had a significant number of projects make use of it and indeed continue to this day. The excellent RISC-V project kicked off at the University of California, Berkeley in 2010. And then the Open Compute project came along in 2011, and I think that's about arguably the first point where there was significant effort made to do open hardware in the context of general purpose computing, something you could stick in a data center, something you could stick in a server rack, that kind of thing, but as distinct from the embedded space. RISC-V RISC-V Foundation, sorry, the OpenPOWER Foundation, good to get that one right. The OpenPOWER Foundation kicked off in 2013 along with the Open Source Hardware Association. The RISC-V Foundation came along in 2015. But we got to 2017 and I guess we started having a little bit of bad news at that point, because that's when we kind of had this fairly nasty series of moments where, as an open technical commons, we learned that we can't trust the hardware on which we've built our software. I'm of the view that we had gone along for quite a long time going, we've got this awesome, as we did. We had this fantastic open source software stack without perhaps giving the attention due to what we were running on. And 2017 was about the point where that perhaps honeymoon stage ended somewhat. Now, I've sort of been conscious of what I've crossed out and what I've left uncrossed out here a little bit, in that my desire here is not to draw attention over much to things like Spectre Meltdown. Power 9 was affected, though not as dramatically, just as much as any processor or speculative execution was. But I think in something like having a management engine on the chip that you couldn't actually switch off was perhaps one of the first examples where we really saw, having that sort of closed design isn't really going to be the best way for us to engineer our systems in the future. So I think as a technical commons, it quickly became clear that there's a bunch of things we really needed to have for our open and fast computers. We needed an open hardware design as far as it was practical to do, an open software stack. It was particularly important that we didn't have any binary blobs, no code that we couldn't inspect, or nothing executing on the platform that we weren't able to inspect to a reasonable degree. No unexpected operating systems or management hardware would be kind of nice, but also good to not have any price or performance penalties. So we don't really want to have this openness at the expense of having devices that aren't actually practical to use in general purpose computing applications. So our community as a technical commons, I think, responded pretty solid. We very quickly had patches available that would disable the management engine in at least some x86 architecture systems, and I think credit is due there to some of the libré-focused vendors in the Intel space, the x86 space, who pretty quickly brought tools out to do that. Purism and System 76 are two that come to mind. Coreboot and other similar projects sprung up to replace the BIOS and firmware on these devices, but particularly on x86 and ARM systems, that still left at least a certain partial amount of either binary blobs or firmware on the platforms that it wasn't possible to replace. But over in the OpenPOWER ecosystem, we were kind of a bit of watching all this with the similar horror to everyone else, but there was a little bit of a sense of, hey, wait, we're all needing these open hardware systems that are fast. Kind of, here's one we sort of prepared earlier. And it occurred to me that it's probably actually a good point to actually say, well, what is this whole OpenPOWER thing anyway? So kind of a digression, kind of not. So who's heard of this? Just a quick show of hands, if I would. I'm encouraged, but also slightly saddened that not every hand went up. So it's but I think that's kind of a little slightly tongue-in-cheek, but a fairly fair quote. So just to look at the open history of PowerPC, because PowerPC, Power, and OpenPOWER are all, I guess, share a common lineage. But 91 was the Apple, IBM, Motorola alliance, who set out to build a RISC CPU in 92. We saw the first tangible fruits of that PowerPC 601, which was used shortly thereafter in the first Apple Macintosh in 1994. So at this point, we've actually got PowerPC production hardware out in the community, and very publicly available. Comes to that, of which more in a moment. 96, we saw the G3. A lot of this development's been done in parallel. Sort of Motorola to bring the parts out of the particular code name, and Apple, as is their wont, would put their own branding on it. But you had the G3 in 96. But there's some interesting intersections, things like 1997, the RAD 6000, which was the start of a range of radiation-hardened PowerPC chips that were used in various spacecraft, in fact, continue to be used to this day. And this to say nothing of a myriad of automotive and other military and other applications which PowerPC was used for. IBM continued their server line with the Power 3, which was released in 1998, and that's, I guess, around that sort of era is one that's particularly close to my heart, because in 1999, around that era, the Power 3 was the first power chip to ever be booted as a SMP system to be booted with a 64-bit Linux kernel, and that was work completed a little later in 2000. G4, the GameCube, there was a point where, if we jump to the next slide, PowerPC derived hardware was actually used in many of the dominant game consoles. Power 4 came along, and that's where the Australian or Canberra-based AusLabs team first became involved. And I think that's one of the first chips that actually did a commercial multi-core CPU. PowerPC 970, the Apple G5, came along in 2002. We had the PlayStation 3, Xbox 360 in 2005. And in 2006 it was kind of a downer, because that's where Apple moved off using PowerPC parts to a different platform, as many of you would know. But it was kind of, and there's a bit of a linux.conf.au sort of twist to this as well, because there was certainly a period in those early 2000s where, if you went along to many of the open source conferences, actually by far the dominant hardware you'd see people using was either a ThinkPad or a Power Mac running often Debian, so it certainly wasn't running Mac OS. But that's also the point where, because Apple was no longer using the PowerPC devices, a lot of the public visibility, if you like, of Power started to went away. Hence my earlier rather tongue-in-cheek reference to its death. The OpenPOWER Foundation was formed in 2013. 2014 was the point where PowerPC 64 moved to, or the standard PowerPC 64 distribution moved from being big endian to little endian. Prior to that point, most of the commercial distros had been big endian based. The decision was taken then to shift to little endian to ease interoperability, and I guess, frankly, to make it easier for bad code to work somewhat more reliably for people who weren't able to deal with different endianness in their systems. 2017 was the release of the Power 9 CPU, which is one of the sort of main current processor architecture. And in 2019, the PowerISA was opened up, of which a little bit more later on down the track. But what was significant there was that the Power 9, or the PowerISA, I should say, became available royalty-free for use in any number of applications. I wanted to take a moment to look at the architecture of a typical OpenPOWER system from a hardware standpoint. And I'm going to do a little bit of show and tell at this point with the audience, with some audience participation. If you can, these aren't a keep one and pass it on, unfortunately, but if you can distribute these around as we go. Keys is looking particularly intently. That's good. So most of the shipping OpenPOWER systems at the moment are actually based on, and certainly the general purpose ones are either based on either IBM Power 8 and Power 9, and what's being passed around the room are a couple of different examples of Power 9 CPUs. One's an actual bare die, the other ones are actually in their packaging. I do make the distinction there about the general purpose one, because NXP are one example of a manufacturer who continues to make PowerPC parts. Those technically they're PowerPC rather than Power. It's a distinction that's not terribly germane to the conversation today, but we'll come back to them in a moment. The Power 9 CPU is a 14 nanometer part up to 4 gig. You can sort of get a sense of the specs there, but it was very much designed as a server grade part, and that's why it's so heavy actually, as you'll feel when it comes around, but very much designed for high performance applications. Most of the so one thing I do want to call out too with Power 9 is it's DDR4 and PCIe Gen 4, and we're actually first onto the market with those. But the Power 9 is a little unique in that it has two different options on chip for cache coherent interconnects, which is a bit of a mouthful, particularly on a late on a Wednesday afternoon. But it was unique when it was released as being the only chip that had onboard NVLink interconnect, so it could do a very fast connection to an NVIDIA GPU without having to go through PCI, and also has the OpenCAPI interconnect available as well, which is an entirely open protocol, of which more in a few more slides' time. The OpenPOWER systems is a bit of a subtlety to the way they're positioned, I guess, but the OpenPOWER systems are either one or two sockets designs, up to 22 cores per socket, 4 threads per core. IBM chooses to make a differentiation between OpenPOWER and Power, where the Power systems that IBM produce go all the way up to 4 sockets, 4 sockets designs with either 4 or 8-way SMT, so much bigger systems, refrigerator-sized systems, obviously, often. The performance design point on these is very much in that mid-high-end workstation up to servers, so these are in no way, shape or form embedded parts. You can crank a Power 9 chip down to about 40 watts, but that's about the extent of it. And it was never really designed to do anything. It wasn't sort of intended to be a low power part in that sense. From a hardware standpoint, with the modern OpenPOWER systems, and this is I think significant to us as a technical commons, is many of the OpenPOWER systems are on the market from a hardware standpoint at this stage are either entirely open hardware designs, either to the schematic or PCB layout, or often based off that. Some are straightforward commercial designs where that's not the case, and it varies a little bit from system to system. And for the sake of a pretty picture, it is kind of cool. So that's basically what's sort of slowly working its way through the room, a micro photo of a typical Power 9 chip. The software side of OpenPOWER is interesting, I think. It's, in most cases, entirely free and open source software all the way from top to bottom. So the open source kernels, compilers, tool chains is a very mature environment that Power, as you saw from one of the earlier charts, was one of the earlier ports of Linux, non-Intel ports of the Linux kernel. The compiler, tool chains, and libraries have been around for close to 20 years and been well maintained all the way along. So the software side of things is very mature, and the compiler tool chain side of things. The firmware and software on the main cores, I sort of went with that sort of set of progressions there. Tried it both way around. That seemed to make most sense. But the self-boot engine, or SBE, is where things kick off, and that's a progression of a boot process throughout, all the way up to either running KVM or running your main operating system. All the standard Linux is supported, and FreeBSD's port is quite mature as well. The FreeBSD port's, I think, a little interesting, and it remains big endian. The chips themselves can do both and can mix and match. But the FreeBSD port by default is big endian. But all the software there is entirely open source. The firmware for the on-chip microcontrollers, so a processor of that complexity has a number of sub-processors on board that do things like power, thermal management, frequency management, and so forth on a chip there. And some of those are actually PowerPC cores in their own right, or close to PowerPC cores, as one of my friends often reminds me. Again, the source code for those is entirely available. And as befits its server heritage its heritage as a server part, there is actually an on-planar or on motherboard controller that provides OpenBMC, so it's an IPMI-like functionality, and that's also entirely open source software as well. So if you recall my earlier premise around to getting sort of open and fast computers, there's this particular set of things that I think we need. I thought I'd just walk us through some of the ones we prepared earlier, or to think about it a different way, a bit of a walk through some existing OpenPOWER hardware. This first system, I think, is arguably one of the more interesting ones, and not least of which because of who collaborated on it. It's a thing called Zaius, or Barreleye G2. It was a collaboration between Google and Rackspace, who worked together to develop this planar, a couple of Power 9 CPUs, a ton of memory, and the option for either OpenCAPI or NVLink interconnects off the board. So you can see the basic motherboard or planar design there was then used by the two companies in one or two different variations in the data center. On the left is the Google design called Zaius, and that fits into the standard Google data center. They have them in production to this day, and as is their prerogative, they're typically cagey about what they actually do with them, but they use them in production. And then the system on the right, which is the Rackspace version, the Barreleye, is actually an open compute design as well. So the section right up the top is a slide-out storage cartridge, and then the two sort of green things you can see in the middle are a couple of NVIDIA GPUs. But it's entirely common planar that's sitting underneath that. And of significance, every single aspect of the hardware design of these is open hardware. So it's an open hardware design, and again runs an entirely open source software stack. Another system by another one of the member companies of OpenPOWER Yadro Vesnin. This is actually a Power 8 design. It's a little different. It does run an entirely open software stack, but by contrast, it's primarily a closed hardware design. It's Power 8 based. It can go all the way up to 384 threads with 48 cores, up to 8 terabytes of RAM sitting in there. So they call it their in-memory hurricane, and it's only that tall. They brought one to a show once in Europe, and they actually left it there overnight, and it occurred to me that because they'd actually brought along one of their pretty much fully populated test systems, I thought that's pretty much the cost of a very nice motor car just sitting there on that, like Porsche kind of levels of nice. But that runs an entirely open source software stack. The IBM AC922, this is an exploded view of one. This is a particularly significant machine because they power two supercomputers called Summit and Sierra, which are the #1 and #2 supercomputers in the world at the moment. The variant, you can see the specs there. I've shown their intelligence by reading through every single one, but there's a couple of variations in the way they set it up. The Sierra, the Summit system uses 2 Power 9s and 6 NVIDIA V100s per node. Sierra uses 2 Power 9s and 4 V100s with different memory, different balance of memory configurations and so forth, but pretty quick computers. But again, an entirely open source software stack on these particular systems. They run RHEL, they run OpenBMC, and I guess a little bit of a shout out to the team down in Canberra at AusLabs who actually did the bulk of the operating system and firmware for these platforms. Inspira-based, one of our members in China, they do a 2-socket Power 9 design they just released a few weeks ago for the China market. Again, intended largely for the server space. Then we come to Raptor, and they're kind of an interesting company. They're based in Chicago, and their entire business model is actually doing owner-controlled or auditable systems. So they were of the view that they really wanted to get serious with making hardware that could be deeply inspected and deeply trusted, and they actually chose Power to do it. It was very much a decision that went that way around. They do 2 different designs. The one on the left is obviously single socket. The other one's a dual socket, the Blackbird and the Talos 2, respectively. The entirety of the software stack on these is open source, and the hardware is all open hardware designs as well. You can literally go, they used to ship it with a CD, but I think now you just go to the wiki. You can actually go to the wiki and pull down the schematics and every level of detail you could possibly imagine for these systems. And they're quite affordably priced. It's not my desire to stand up here and sell you stuff, but these sorts of systems are available at a price point that's pretty comparable to not quite running down a Fry's or Newegg or JB Hi-Fi or whatever and buying a motherboard, but getting pretty close. And certainly for the performance you get there, they're really quite impressive. And the system on the left, just a little plug for the raffle while I'm at it, but the system on the left in the case is the one that's available, is being raffled off at the end of the show. But they're again entirely open source both in the software and the hardware. So I guess these are the systems we were talking about. We were watching the need in the community. So we've got this premise of we need open hardware now, and what are we going to do about it? I think from a high performance standpoint, we've actually got a lot of that there. In the OpenPOWER ecosystem. So common questions: where's a laptop? Well, Power 9's. You've all pretty much probably by now felt one. That's not really going to work in a laptop. It wasn't. It would be a good weight program. You can just imagine it. Yeah, it's. In fairness, it was not what the original design point was. But it's quite an interesting project out of Europe. The PowerPC Progress community are building a laptop design, actually based around the NXP T2080. Now, as the purists would rightly point out, it's not strictly OpenPOWER. It's actually an earlier version of the ISA, and the T2080 is designed as more as a communications processor. So it's quite high I/O performance, but not necessarily super high compute. They're using the Slimbook eclipses and mechanics for the design, so they don't have to re-engineer that. And they're in the process of crowdfunding their PCB layout, and last I checked, they were about a bit over a quarter of the way to the 24k euro goal they had to get the PCB done for that. There's more details there. I commend it to you. It does look like a pretty good project, and I've been fortunate enough to speak with the team behind it a couple of times, and they really do seem to have their head screwed on, and I think they'll accomplish some pretty great things with it. So I kind of glossed over a fairly significant thing earlier on in talking about the OpenPOWER ISA being royalty-free, and I thought that might be a good one just to expand on and talk about openness in a slightly greater level of detail. The slide's a little bit of an eye chart, but essentially what was announced back in late August, IBM and the OpenPOWER Foundation got together, and on this particular announcement, and what IBM did is they took the Power ISA and said, look, you can use it royalty-free. So go take the ISA, all the information that represents, and go ahead and start building chips. Do whatever you like. They went a little bit further, which I think was a sensible move, in that they made it very, very clear that if you wish to build, or if you're building an implementation that's properly compliant with the ISA, they would actually give you a license for any IBM patents that relate to the ISA itself. Now, I always feel a bit dirty, actually, talking about patents in a room like this. But it's significant when you're building chips. There's a big investment, and you need to know that basically no one's going to come after you. And I think that was IBM's logic in making that very clear from the outset, that if you're building something based on the ISA, that they're not going to come after you. From an OpenPOWER Foundation standpoint, the organisation that I work for, we're in the process of standing up a work group. Excuse me, just 1 second. That's so much better. Excuse me. So we're in the process of standing up a work group with the OpenPOWER Foundation to oversee the ISA, and so we'll actually have, I guess effectively control and responsibility from the ISA from here on in. And that'll actually also include the ISA as gets used by IBM and anyone else for building parts. It'll include a way for changes to be made to the ISA, and we're still working out the finer points of that. But one of the things that we're particularly keen to avoid is fragmentation. So as I'd mentioned earlier on, the OpenPOWER software ecosystem is really nice and mature. It's been around for 20 years. You look at the architecture, it's really nice and clean. We don't want to cock that up. We want to keep that nice and consistent from here on in, but allow people a way to engage, contribute to it, and have input. Back during that same announcement, IBM also announced the release of RTL. That's the low-level hardware designs for the OpenCAPI and Open Memory interfaces. These OpenCAPI has actually been used in production for quite some time. Unlike many competing technologies, OpenCAPI provides a way to connect accelerators cache coherently to the processor at very, very high speed. Open Memory, or OMI, Open Memory interface is actually likely to be pretty much what we see after DDR5, DDR6 sort of time frame. It'll be a replacement for those technologies, and the RTL for those is being made freely available. And just a footnote, because it was kind of a big deal for us, is that we moved the OpenPOWER Foundation to be part of that, to do our management functions through the Linux Foundation. Yeah, it was all right. Excuse me, sorry. So I want to talk a little bit about, because the question often comes up about what about soft or FPGA cores. At the same time as the announcement of the opening up of the ISA, IBM also announced the Microwatt project, which is the brainchild of a couple of IBM engineers here in Australia, Anton Blanchard, Mike Newling, Paulus, and others. But this is basically a 64-bit FPGA implementation of the PowerPC architecture. It was integer only. It was done as a proof of concept, just to essentially to have something out there, but it's already taken on quite something of a life of its own. But in August 2019, it was demonstrated running MicroPython, and it's spurned so much interest already that there's already a blog post that was very quickly followed with a blog post from the community on how to add instructions. And so it's kind of what was intended as a proof of concept has taken on something of a life of its own. There's been quite a lot of interest in Microwatt. The MicroPython port, as I mentioned, there's been a bunch of optimization work that's been done on it since the announcement back in August. Paul McCarris, who's here in the audience today, at risk of embarrassing, and Ben Herrenschmidt, who I imagine, yes, there's Ben, took the original design and basically managed to sort of half the number of LUTs that we used and make it go twice as quick at the same time, which was pretty impressive. Shortly after that, we announced it's now at the AR event in Europe in October. We had the Zephyr port running on the FPGA, and unfortunately I diligently left my FPGAs back at my hotel room, which is a strange thing to do, but these are running on small boards like you saw on the previous slide. I learned on Monday actually that we now have a Rust port and a port of P4 from a couple of members of the open source community there, and I think of significance is we're very close to being able to compile and build the Microwatt implementation on an entirely open source FPGA toolchain, which is something we would very much like to see from a community standpoint. At the moment we're battling with the same commercial tools that many people do, and I think the sooner we can get onto open source ones, the happier we'll all be. So trying to draw a few conclusions together from all this. I think open source software proved to us that open is the way to go for security, for flexibility, and indeed for performance. The issues we saw in 2017 in particular demonstrated that to make the most out of open source software, we really need to have open hardware as well, or we don't know what we're running on top of. Shout out to our friends on the RISC-V project. The solutions in the embedded and medium performance range are really well known, and RISC-V is just doing amazing stuff in there, and I hasten to emphasise here, I don't mean either those embedded or medium performance in a pejorative sense. It's just different aspects of the same sort of ecosystem. But to answer the question as to how close we are to get truly an open fast computers now and in the future, I think there's a strong case to be made that actually what we have in the OpenPOWER ecosystem now is very viable already. Just want to talk about the OpenPOWER Foundation really quickly, because that's actually where I work and they pay my salary and other appreciated things like that. Our overall mission is actually to promote the OpenPOWER ecosystem as a whole, and from here on in we'll also be stewards of the ISA itself, working with our member companies. It's a not-for-profit technical consortium, a members consortium, and while many of our members, 350 members we have are corporations, and academic institutions, we very much welcome individual members as well. It's free to join, and that gives you the opportunity to be part of the work groups and so forth. We do try and do as much of what we do out in the open. Nonetheless, there's details available on the website. I think we've got a few more minutes left. So I think a couple of things I wanted to finish on in terms of future thoughts. I think for Microwatt and open ISAs generally, the emphasis we will see for this year will be moving to open tooling. Tim Ansell has been a great proponent of open tooling for FPGAs, and we see that as being integral to the overall success of open hardware at that lowest level of the stack. From an OpenPOWER standpoint, we had after the announcement in August, we had an enormous amount of interest in companies, and many of them you would know the names of very, very well, who are interested in building implementations based on the ISA, and many people are saying, well, hang on, why am I paying a license fee for a commercial ISA when I've got this other one that's actually free? And I guess we politely have to say, well, that's something they need to evaluate. But my sense is that in the course of this calendar year, actually, it's very likely we'll see at least the announcement of some accelerated designs based on the OpenPOWER ISA, and perhaps some general purpose CPU designs as well. Kind of all the pieces are there. I think as a more general point on the whole process or whole aspect of doing silicon implementations, making chips, it's actually a hard process. We've done extraordinarily well as an open technical commons, building the best operating systems and other tools in the world at the software level. What's become very apparent to me, even in the short time I've been involved with this, working with chip designers and others, making chips is actually properly hard. Like, it's not to say making an operating system kernel is trivial, but we at least have the advantage with the Linux kernel. If we get it wrong, as I often did back in the day when I was coding, you can just make and recompile and off you go. That's considerably harder to do if the output of what you're doing is a mask that costs several $1 million to fabricate, and it's not until you get back and go, oh bother, sort of thing. Now there's clearly different things that we can do to implement that, but this is where I think the focus we're starting to see in the overall open ISA community around tooling and compliancy and verification is going to be so critical to us. And what we're hearing from some of our member companies who have a lot of the expertise and a lot of tools in that regard is a desire to actually make those more generally available, so that all the different open ISAs are able to leverage that and make use of that, sort of all boats rising with the tide. And in particular, the validation of silicon, and this is where I think almost a philosophical level. It's something where there's an open technical commons we need to start to reason with. We can inspect a printed circuit board pretty readily, and we've seen some exciting things that have had to happen there. But it gets considerably more difficult and say, okay, well, I've got VHDL or whatever the output is of my tool chain for a chip design. How do I verify something that's only a few nanometers wide? That's going to be an interesting, not to say it's impossible, and I mean you can sit there with an electron microscope or similar technologies and do it, but that is quite complicated and quite time consuming to say the least. So I think we need some more smart minds on those sort of problems. That's pretty much all I had in terms of some prepared material. I'm absolutely more than happy to answer questions if there are any, or given that I'm probably the only thing between now and... I'm 10 minutes over, or? No, we have 10 minutes. Oh, okay, good. All right. Awesome. So happy to answer any questions if people have them. Oh. Uh-oh.
So you said way back in the presentation that the two top supercomputers were running fully open BMC, fully open everything. Was that a requirement from the customer, or was that just something you wanted to do to prove a point?
No, actually, as I understand it, that was actually a requirement from the US government as the customer for that. I'm going to extrapolate slightly further, if I may. My impression from what I see from our foundation standpoint is that that's becoming increasingly common. We have the good fortune to work with some really interesting initiatives in Europe, including groups that are actually wanting to do, as an example, open accelerator designs, and they are really appropriately, and to their credit, pushing pretty hard on that. It's all got to be open. I think actually Europe leads us in a lot of respects on that. But yes, in the case of Summit and Sierra, yes, it was, as I understand it, was a requirement. Please. It must be running an ARM CPU in that, I guess. Oh, is this on? Yeah, it probably is true. Please, and I'll try and repeat the question.
Any given system will obviously contain multiple components such as NICs and HPAs and hard drives.
Yep.
So what's your outlook on having this complete system open?
Sure. So the question was that in any non-trivial system, it's not just the CPU. You've got that disk adapters, Ethernet controls, and so forth, all of which have silicon in them. And how far can we go open? I think, is that a reasonable... Yeah. No, that's a really, really good question. And I think actually we need to go as far as we possibly can at the moment on many systems. I'll pick on the crew at Raptor briefly. Sort of, at least for them, there's no firmware, no binary blobs, anything like that. But you can't actually look in the chip on any of it. And that includes Power 9, to be fair at the moment. And this is where what's happening with RISC-V and other open ISAs, I think, is really, really exciting. The CHIPS Alliance are doing a fantastic job of building up a library of open IP blocks, intellectual property blocks in different forms, to build all those common system components, Ethernet controllers, UARTs, memory controllers, caches, all those different pieces as open design. So I think it's entirely feasible for us to get to the point where the motherboard you saw earlier, basically everything that's populated on that is actually based on an open hardware design. Our ability to take those open hardware designs and correlate that to the actual silicon is a much, much more complicated problem. But yeah, I think there's no reason why I can't. And credit where credit's due, that's an area where the RISC-V ecosystem is doing a great job. A lot of those boards are pretty much open. Or the SoCs are sort of open all the way up to the edge. Please.
Just curious, you mentioned trying to go drill down into the hardware and the CPU to like gate level or whatever. Are you aware of anyone implementing or doing a test implementation or an exploit at that level, like the whole C compiler nuke thing or whatever?
Not directly, or not directly aware, and it kind of feels like it might. If I were one of those, I probably couldn't tell you, kind of thing. But I think there certainly have been exploits seen in the wild where people have put funny things onto the die, but it is pretty complicated to do. It's a very closely guarded manufacturing process because of the sensitivity of it, and I think there's a number of credible open source endeavours to minimise that. At larger feature sizes, that's relatively easier to do because you could conceivably stick it under an electron microscope or similar, but much beyond that, it's pretty tricky. I think as an ecosystem of software and hardware engineers, that's where we need our brains to think, well, what are our provability sort of axes there? Please.
Yeah, thanks, Hugh. I'm probably showing my ignorance here, but kind of related. How important is like an open microarchitecture along with an ISA for trusted computing?
For trusted, no, I think that's exactly the thing. Is that sort of an open ISA gets you a lot of the way because you can sort of at least see what's going on, contribute and so forth. But yes, the microarchitecture, which is the specific implementation, is the bit you really need to see to understand how the gates are flipping and so forth. Most but not all of the RISC-V implementations, as an example, are open microarchitecture designs as well. Power9's not at the moment, but the Microwatt FPGA implementation is, and anything that's out of that FPGA VHDL space will become so. And my impression from talking to our members who have built power chips in the past is that there is an interest in making previous microarchitecture implementations available as well. Any other questions, comments?
New question there. So that Raptor board that you showed there,
yep.
If I was to get that board and put it into a case and run it as a server, is there any other particular hardware that this stuff needs to go, or can that run off just regular server grade?
That's the beauty of it. It's all standard stuff. Like I went to it's DDR4 memory, PCIe Gen 4 interfaces, standard SATA slots, all that kind of thing. It is. That's the ironic thing in a lot of ways. You look at the motherboard, and other than the CPU itself, it's all just bog standard. They use Broadcom Ethernet chips. So I got most of my bits from random computer shop in Melbourne and stitched it all together, and was greatly relieved when it switched on. I hasten to add, due to my ability to be incompetent, not any quality of the design. Please.
So the screwdriver to attach the heatsink is probably one you don't have.
Yeah.
But they sell that together, it's fine. Otherwise, yeah, I did the same thing, all PC parts.
And it's one you probably don't have because it's like 3/16 of an inch or something like it.
It's something weird like that.
Yeah,
long because it has to fit.
Yeah, it's long because it's got to go down the way.
And suddenly you go, oh, this is really elegant. Why doesn't everyone else do something like this?
Yeah, it's like, but it's the way it's documented. You think, oh, I'm going to die. I'm going to like crush it, and then you go type. Cool. Any other questions, comments?
There was a big gap in your timeline between 2006 and 2013,
yep.
which is basically between Apple and, was it the OpenPOWER Foundation at that point?
Yeah.
Yeah. And then there's a long time between 2013 and 2019 when the ISA was announced. What happened? There's all sorts of politics and stuff involved and business decisions, but why did it take quite so long?
I think in that sense my timelines were possibly left out. I mean, it's just more how much can you pack in. But it's a fair question. At the point where Apple stopped using PowerPC chips, I guess IBM was at Power 5-ish in their design. For example, they did a 6, a 7, and 8, and just done a 9. I consciously left those out because it just gets a bit monotonous. There was an initiative previously to somewhat similar to the OpenPOWER Foundation, and that's called power.org, and that sought to do some stuff in an open way for various different reasons that I'm actually just genuinely unaware of because I wasn't involved at that point. That didn't proceed, but it's kind of why I put it as a tongue-in-cheek sort of thing, the rumours of my death kind of stuff, like actually IBM kept building kick-ass, amazingly good systems out of their power range of parts. It just wasn't actually visible. The decision to set the OpenPOWER Foundation up in 2013 without wanting to sound like an ad was actually IBM's first step on, I think, on that open journey. We've got this really cool technology. How do we get other people using it? Oh, well, we'll make the CPUs. We'll get do all the designs around it to be open and start building systems. And went from having one company making Power 9 or Power 8 as it was then base hardware to suddenly got half a dozen or more and 40 or 50 different server designs and so forth. And that's kind of where we are now.
And so that was the more kind of traditional company consortium thing?
Yes. That was a more traditional. But traditional other than the inputs now. Well, the outputs were all open source. So in fact we still have them in the work groups to define things like the OpenCAPI interface and the other ways. The OpenCAPI interface, even though it's not strictly an OpenPOWER thing at all, was actually kind of an interesting early example of the intent of what they're trying to do, because OpenCAPI was going to be built on power CPUs to begin with, but IBM and the groups involved actually put the effort in to make things like the cache line sizes and all the other technologies work for all the other architectures, so you could conceivably use that with any other chip, and that's what they're hoping. And that was done back in 3, 4, 5, if not more years ago now. So
there have been more outputs, there's been things going on.
Yeah, and I see it, my feet get sore because I stand at trade shows, and it's a common sort of, the genesis of the conversation we're having, Jeff, is not dissimilar. Oh, I thought PowerPC had gone away. Oh, no. Yeah. Any other questions, comments? If not, I think, was
Last question.
It's probably a slightly broader question for you, but how do I know that the chip that I'm getting is actually a Power 9 chip? Because we know all the issues with fakes and all sorts of other bits of hardware.
Yeah, that's a good question. I think that's hard for any microprocessor. I think it's pretty hard to make a counterfeit 14 nanometer 6 billion transistor part. But the genesis carry of your question is nonetheless.
Has it been modified?
That's where it gets tricky. I think my personal opinion is I think at the point you're dealing with adversary that's that competent, they're probably going to find other ways to find out what they want to know anyway. I think we're about done. Look, thanks for your attention this afternoon, and particularly this late in proceedings. Do appreciate it.
Thank you, Hugh. I think we're all looking forward to winning that board in the raffle now. So
Well,
go to the website and buy raffle tickets.
Yeah, I meant to say, there's actually a whole system.
And a small appreciation.
Appreciate it.
Thank you very much.